Alright, hello everybody, and welcome back for another physics video. My name is Seokhyun, and today I will be talking about dynamics. Dynamics refers to the study in physics and classical mechanics that deals with the forces that are applied to a certain object and how that changes the movement of the object. So let's first get started with what a force is. A force basically is something that push or pulls an object. Basically, it's anything that you feel as a push or a pull, or anything along the lines of that. For example, if I lift my book, I am exerting a force on the book that makes it go up. Um, if you throw a ball, you're exerting a force on the ball that you throw so that it goes in a certain direction. And because of this, a force is known to be a vector quantity so you need to draw that little arrow above there, um, as you might recall from the video on vectors that I have done. Um, so that's what forces are. And there's the unit of forces that we talk about are in newtons. And why is it in newtons? Well, the first time that somebody ever thought of forces was Sir Isaac Newton. He's basically the father of all classical mechanics, kinematics, dynamics, whatever you call it, whatever. Newton probably contributed a big part to that field, and that's why we use Newton often for things like forces and whatnot. So you might know the story of Newton with the apple, where he was sitting under an apple tree. The apple fell down. Newton thought, that's pretty interesting. Why did the apple just fall down from a tree? Right? So it turns out that's how he discovered gravity, right? And basically, the force that the gravity exerts on the apple that fell down was roughly how Newton defined 1 Newton is about the mass of an apple and how much force gravity applies to that apple is 1 Newton. And because Newton basically founded dynamics and he's a big part of it, he made 3 laws of motion that really are critical for the study of dynamics in physics. The first law, as you might have heard, is the law of inertia. What does it state? Well, it states that a object in motion wants to stay in motion until an external force is applied to it. Now, what this means is that if a car is going to be moving down a highway or something along the lines of that, and you have it going at a certain speed of, for example, 60 miles per hour, the car would want to go at a speed of 60 miles per hour until you hit the brakes, and that's when it starts slowing down, right? This is what Newton's law shows. It's that if you, for example, if you open a door and then you just let go of the doorknob, it's gonna just swing, right? It's gonna swing to the direction that you opened it. Unless obviously the door has some restoring forces that we'll talk about later, but the door will swing open until you hold it back, right? That's the law of inertia. An object in motion will want to stay in motion until an external force is applied to it. This also applies when the object is not moving. So you need to move something that's just sitting on your table, right? It just doesn't move on its own. You need to apply an external force to it so that it moves, right? So the object in motion also encompasses an object that is not moving at all. We consider that to be a motion which is not moving. Um, so that's Newton's first law. Newton's second law is what connects dynamics to kinematics. And this is the world famous equation F net equals ma. This is the world famous dynamics equation. You probably have heard of it before, even if you have not taken a physics class, maybe you haven't. But this is the equation that links dynamics and kinematics. Why? Because dynamics is the study of forces, right? And in kinematics, as you might remember, we talked a lot about acceleration, velocity, position, and stuff like that, right? So that's how you connect dynamics and kinematics. F net equals ma. Notice that both acceleration and the force are vectors. So when you're trying to link these two together, you really need to make sure that they're in the same direction, or else this equation will not stand. Um, just keep that in mind. That's Newton's second law. And the third law, which it's called the action-reaction law, which states that every force that you apply has a reaction force. For example, if you are pushing against a wall, right? I don't know if you have ever done this before, but if you push against a wall, your arm feels fatigued, right? Like you feel like something's pressing into your arm and your arm's kind of getting compressed, right? That's the reaction force of the wall on your arm because your arm is pushing against the wall, right? So your arm, the force of your arm pushing on the wall has a reaction force of the force of the wall pushing on your arm. Now, it's really important that you know this really well. Um, for example, we'll talk about this a bit later, but there's a very common misunderstanding between the action-reaction pair of gravity, and if you just let go of a ball, the gravity is pulling the ball down, but if you have a surface, it's not going to fall down, right? And that's what a normal force is the force that a surface applies to an object so that it doesn't fall down. The normal force's job is to make sure that whatever object it is does not fall down beneath this surface, or lift off. If it lifts off the surface, you don't have a normal force anymore. But if there is a contact between this object here and the surface at some point, there will be a normal force that applies from that surface to the object. Okay? Um, and commonly it's misunderstood that when a ball is sitting on a surface, obviously gravity applies to it, but also the normal force applies to it. And these two cancel out, and that's what makes the ball sit on a table, right? And some people might think, hey, the normal force must be the reaction force to the gravity, right? Because they cancel out. But that really isn't true. Because the force of gravity is the force of the Earth on the ball, right? Right? It's the force of the Earth pulling on the ball, to be exact. Let's say that's a ball. So, if we use our analogy here, the reaction force to gravity is force of the ball pulling the Earth. Now, I know this sounds kind of counterintuitive and it doesn't really make that much sense, but trust me, this is what it is. This is called universal gravitation. We will cover this later on later in a different video, but just keep in mind the reaction force to gravity is not the normal force. And that leads us to gravity. I've already explained a lot of gravity. It's the pull of the Earth onto an object. That's basically what we call gravity. And the force of gravity we can write this as m times a, right? Where a from Newton's second law. And this A is commonly known as G, or the gravitational acceleration constant, which normally is 9.8 meters per second squared. So whenever you want to find the force of gravity, you just need to go m times 9.8, where m denotes the mass of the object. So that's how you find the force of gravity. There's a couple other commonly used forces, and one of them is tension. So what tension is how is the force that a string or a rope or something like that applies so that it doesn't stretch or break. That's the definition of tension. It's so that the rope doesn't extend in length. For example, if you're hanging a ball on a long rope, the ball would naturally want to pull the string down, right? If you don't hold onto the string, what's going to happen is that the string is just going to fall down. But now you're holding onto the string, so this string wants to maintain its length due to Newton's first law, and that's what the tension does, is that it prevents it from stretching down and extending its length. So tension is the force that resists stretching a string. This is commonly used in problems as well, so it's good to know. Now, we can't really know the magnitude of the tension. We need to be given specific circumstances, and I will talk about how we would find those later on. Um, the last force that I want to talk about is friction. Now, friction is a bit more complicated. Let's say you have a block on some surface, right? And you're trying to get the block to move in this direction. Now, you might know that if you're trying to push a heavy box, you have a really hard time getting it to just start moving, and then at some point when you exert enough force, the block just starts moving, right? That's what's called static friction versus kinetic friction. So friction, by definition, I should have said this first, is the force that opposes movement on a when it's, and obviously friction needs a surface to resist the movement, so it needs a surface so that the surface kind of pulls on the object that you're trying to push, and that's what causes friction. Now, going back to our discussion on static and kinetic friction, what static friction is the friction that applies on the block when it's not actively moving or accelerating. So when the block is just still, it still takes some force for us to move it, right? We can't just like apply minimal force and expect it to move. When we apply only a small amount of force, the static friction basically just cancels it out. There's something called the maximum static friction, which is the minimum amount of force that you need to apply to get the block to be moving. Basically, static friction, this might make it a bit simpler. Static friction makes it so that if you apply a small force, the block doesn't move. But once you apply more than what's known as the maximum static friction, then the block can start moving. And that's when the friction turns to kinetic friction. And this kinetic friction value is always constant. And this is, it's mu, the Greek letter mu, times the normal force. The Greek letter mu is just constant, and it differs based on what material the block and the surface is made out of. You might notice that if you're on ice, there's very little friction, for example, whereas if you're on a carpet, there will be a lot more friction. That's what mu does. It distinguishes what material you're on and how that would affect the movement. So we can draw a total amount of force applied to the force of friction. There's a really cool graph where if you apply force until the maximum static friction, let's say this is a maximum static friction, the force of friction matches the force that you have applied to the object. Right? If you think about it, if you try and push a really heavy box and you can't get it to move, the box doesn't push you back. I mean, the box does push you back, but the box doesn't slide back. Um, if you have more friction than you're applying, it implies that the block is just going to slide onto you, and that doesn't really make that much sense. So that's why the force of friction until the maximum static friction is same as the force that you have applied. However, if you go over this, then the force of friction is locked at mu times the normal force. Normally, the value is lower than the maximum static friction, um, but yeah, that's basically how friction works. Now, you might wonder, okay, so how do I apply this to a problem and use these forces, right? You need to know something called a force diagram. What a force diagram is that you take an object that you want to look at and you write down all of the forces that are applied to it. Let's just say, for the purposes of this, we have a block on some sort of table and we're pushing it with a force F. Okay? How we draw the force diagram is that we take the block, we know gravity always applies, we know there's a normal force, right, because there's contact. We also know there's friction. Oh, something to also note. Friction always opposes the direction of the force that's applied. It's kind of implied in the definition of friction that it opposes movement. So it always is going to oppose the direction of which you apply the force to, or where the block is moving. So in this case, since we're applying force to the right, the force of friction is going to be towards the left, and you're going to apply force here, right? So this is what is known as a force diagram. You will have to draw this a lot when you're doing problems, and normally you'll know the acceleration of the block, or the total distance moved over time, or whatever. You can figure out the acceleration of the block based off of what the problem gives you. And what do you use? You use Newton's second law, F equals ma. And there's a reason why there's a net. That's because you want to analyze the quote-unquote net force on the block. What does that mean? Well, if you take the forces here, right, there's just four forces. So what we want to know is what is the total force that is being applied to the block, right? In this situation, the force that's going to be applied to the block is F minus the force of friction towards the right, and the normal force minus the force of gravity upwards. And from these two equations, you can find the acceleration of the block, and from there you can solve problems using the kinematics knowledge that you probably already have. Thank you for listening and watching this video, and next time we will talk about universal gravitation and oscillations.